Hello everyone. Here we'll talk about the basics of the transformer algorithm that is key to the large language models like ChatGPT or Claude. Well, generative AI first is the subset of AI technologies that can generate new content, isn't it? It can this leverage complex algorithms to understand patterns, styles, or logic from vast data sets, right? Okay, so I guess you have seen enough in recent news. They both uses neural networks, like deep neural networks, and they have say, taken some several concepts um, from like the neural network autoencoders and things like that. So it has a long history that that has from text-to-text language model or translations and these kind of things. And the deep learning basically made it supercharge these technologies. So eventually it became like the GPTs and then all this, especially like the transformer model was very um, pivotal in this kind of development. Yeah, so which is what we'll talk about here. But also, there are also the other techniques like generative adversarial networks by Ian Goodfellow, and DALI and stable diffusions and many things. It basically is a subset of AI technology that generate new content. Okay, All right. So there are many things that you can do, but we'll see more in the multimodal for this text to image and these kind of things. Um, and yeah, so I guess so here we'll just skip these things and go to the transformer. So this is a transformer algorithm. It's relatively simple. We embed the input and then go to the multi-head attention and then feed forward and have several of them until we go to the softmax output. Okay. And so here's another way of viewing it for the diffusion models. Okay, so how the transformer works. Um, Basically, it started as a machine that produced probability distribution over the next word guessing. Okay, and eventually it can predict more than just the next word. And at the core, um, it has these basic features. Like first, of course, we tokenize and embed the input sentence, and then we track the position of each word in that order. And that is very different from the traditional natural language processings like bag of words model, where they just count the words and orders are forgotten. Okay. And then we have the attention layer, which basically gets the correlation between pair of words and which are most correlated, sort of more relevant to. And then we have a feed forward layer. Um, and then we have the output head to get the probability distribution over vocabularies of what might come next. Okay. So the first step is tokenizing. So tokenizing means that converting a word into some kind of number. So in this particular case, we are making up, but so the rate is like zero point 0.9, zero point 0.1, 0.4, 0.7 in a four-dimensional space. In reality, like GPT-3 uses more than 12,000 in dimensions. So this is just a simplification. The will have these numbers and rise will these numbers. So in just simply just show you. Um, so like rate will rise will look like this. Okay. And you can run it and it will run. Mm, okay. I guess it's the first time the cell running, so it'll take a few seconds. Let me just make sure I ran everything. Yep. Okay, so you can see that rates will rise just like this figure it shows here. And then we add the positional signal. So the embeddings alone these embeddings don't carry the word order. Rates will rise. It's very different from rise will rates or something like that. So the position is important. So the detailed mechanism, if will have a different lecture about it, but we basically have some positions encoded, and the positions are then added to that. So we do this. So once it remembers where the words are located within a sentence, then we go to the attention layer. So here what it is that essentially rate will rise, is attending from, and then which word is it looking to? So the relative relevance to it. And you can see that more than will, for example, the rise is connected to the rates here, for example. Okay. Something like this. Again, we'll walk through the details of how this mechanism works, but just to highlight here that the attention is about correlation between two pairs of words, which are most relevant, sort of um, heuristically speaking. So here is the attention matrix. Okay. So the original input vector, and after the attention, multiplying it out, it will look like this. And then we have a feed forward layer. Um, that processes each token independently. It's a per token interpretation step, okay? All right. So the rates is processed like this, will like this, rise like that, okay? And in reality, like GPT-3 has 96 layers. It's just a simplified heuristic illustration here. And then we have the output head, which predicts the word. So this is the final hidden state of the last token, and project onto full vocabulary using a linear layer of the softmax to convert raw scores into probabilities. So there's a probability distribution. And then, so over here, for example, the rates will rise sharply, something like that will predict it the most, for example. So, and encoded will look like this. Okay, sharply is kind of the highest one. So this is the summary. So we'll have basically from the encoding to the output softmax to have everything coming out. Okay. Why the transformer replaced the RNN in finance? The long range dependency between words. So in a sentence could be long, and then um, the distant word may be very importantly connected than the next word, and NLP traditionally forgets about the order. So this kind of thing was better. And all tokens are processed simultaneously. This is why you can actually take it. Okay, and then there's the transfer learning aspect of it, uh, that you can transfer part of the trained network and then bring it here. Okay. Okay, so this was just a brief overview of what the transformer overall does, and we'll take a look into this detailed mechanisms of positional embedding and attention, especially in later episodes, um, to see how they actually do these kind of functions. Thank you for watching this episode.